Hi, this is Mrs. Mays. Welcome back to AP Chemistry. We're still working on equilibrium. This time we're going to look at the type of calculation where K is neither very high nor very low. For this type of calculation, I like to use my solver. So let's get started here. So here's our situation. We're going to combine nitrogen and hydrogen to form ammonia. This is a balanced equation we've seen many times before, and we're given the equilibrium constant for the reaction at 500 kelvins. Then we have initial concentrations given for nitrogen and hydrogen. This must mean that there's no ammonia there yet, since the reaction hasn't started until we put the two things together. Remember, when we have a K that's this big, using the small x assumption doesn't really work because we're going to form some product and it's not going to be a small amount. It's going to be a significant amount. So this time when we use the solver, when we make our guess for the value of x, instead of being 1%, we're just going to call it 1. I mean, heck, that's a good place to start, right? And then you'll push alpha solve after you type in your guess for x and the equation will work itself out. So let's get started. First, write your balanced equation into the rice table. That way we can use the mole ratios to do any stoichiometry that we need to. And of course, in this column where my equilibrium arrows are, we're not going to put any numbers in there. So the initial concentration was, let's see, 2.3. Sorry, I got all distracted. 2.3 molar for nitrogen and 1.25 molar for hydrogen, and of course 0 when we don't have any products yet because we didn't start the reaction yet. Great. Our next step is to see what's going to happen as the reaction proceeds. For instance, my reactants will go down by some amount, and whatever the nitrogen loses, I'm going to lose 3 times that amount from my hydrogen because that's the mole-to-mole ratio. So as the reactant quantities go down, my product quantities will increase twice as fast as what the nitrogen is going down, because that's the mole ratio for nitrogen compared to ammonia. So let's add the numbers together to get our equilibrium values. 2.3 minus x for nitrogen, 1.25 minus 3x for hydrogen, and just 2x, right, for ammonia. Ammonia is 2x. Now let's write the equilibrium expression so we know what to do with all of these numbers. Ammonia is going on the top, and that will be squared. On the bottom, in the denominator, I've got my 2 reactants. Nitrogen is to the first power. Hydrogen, though, is raised to the 3rd power because it has a 3 in front of it. Now I can put my numbers in. 2x is going to get squared. And down below, for nitrogen, I have 2.3 minus x times 1.25 minus 3x. And normally with the small x assumption, I can just, oh wait, that one's cubed. With a small x assumption, I can just get rid of anything where I'm adding or subtracting x. But I can't in this case. My equilibrium constant is too big, and so I can't say, well, x is going to be insignificant. It may not be. It's likely to be fairly significant. So let me set this equal to the value that we already know for the equilibrium constant, 4.35. Now I'm going to rearrange the equation by multiplying the denominator across. So I multiply this by 2.3 minus x and 1.25 minus 3x cubed. And then that's gone out of there. Then I'll have to subtract this away because I want 0 over here. So I take this whole thing minus 2x quantity squared. So let's see what happens when we put this into our solver. We're going to try and get a value for x. So I go to Math and find my solver, and I want to clear it out. Okay, and I'm setting that equal to 0 in my other equation. And now I push enter so that I can put in an assumption for x, which will be 1. And then I want to use alpha solve to evaluate my equation. So I get 0.301 molar. Okay, so after all of this, we've determined the value of x to be 0.013 molar. Just clean that up and give me some space. So 0.301 moles per liter is the value for x. But that doesn't answer the question. The question says, what are the total concentrations of all species once equilibrium has been established? So first let's work out the nitrogen value. So I need to take 2.3 minus x, and I can do that with my calculator because it automatically stores the value of x in there. So quit out of the solver. Now I'm back to my normal screen. So I do 2.3 minus my variable x and enter. So nitrogen is 1.9989989. So where do I write that down? Let's just call that 2 molar because I only get to keep 2 sig figs. And then the value for hydrogen is going to be equal to 1.25 minus 3x. And we can let the calculator handle that math for us as well. So 1.25 minus 3x. Enter. 0.3467. And I get to keep 2 sig figs. So let's call that 0.35 molar for my hydrogen concentration. And now my ammonia, NH3, is going to be 2 times x. Calculator time. Nah, I don't need a calculator. It's 0.30, right? So 3.3 times 2 is 0.6. There's all of my equilibrium concentrations. And then the total concentration, you could add these all together. I never have when I solve this problem. I guess I interpreted it as in just getting all of the concentrations, but now I'm tempted to add them together. But you get the picture. You see how to use the solver to solve an equilibrium problem. Build your rice table carefully, and it should all work out. Next time, we'll work on a different scenario with a different kind of K.